Have you ever wondered what it takes to bring a product to life? From the smartphone in your pocket to the car you drive, from a life-saving vaccine to the biscuit you have with your tea, it all begins in a place of immense complexity and precision, the factory. But a factory is so much more than just a building with machines. It's a living, breathing ecosystem, a carefully planned city dedicated to creation, where every movement is choreographed, every process is optimized, and every decision can impact the final product that reaches your hands. In this session, we'll pull back the curtain on the world of modern manufacturing. We will explore every critical decision, from the grand strategy of where to build to the microscopic details of how a single product flows through the system. This is the science of plant location, plant layout, and material handling. Let's begin with the fundamentals. A factory is a purpose-built facility designed for one thing: the systematic transformation of raw materials into valuable goods. Academically, we view it as an integrated production system. Think of it as a living ecosystem, a delicate balance of interacting parts. The machinery acts as the powerful organs, performing the heavy lifting. The workforce is the intricate nervous system, providing skill, control, and adaptability. The materials are the essential nutrients, flowing in to be converted. And information systems are the brain, the central command coordinating every single activity. A disruption in any one part, a machine breakdown, a labor strike, or a supply chain hiccup, can ripple through the entire system, impacting efficiency, quality, and ultimately profitability. In a diverse country like India, factories take many forms, each tailored to its purpose. You have flexible job shops in Pune, creating unique custom machine parts where no two orders are the same. You have massive mass production plants like Maruti Suzuki in Gurgaon, churning out thousands of identical cars with incredible speed and efficiency. And you have continuous process plants like the Reliance refinery in Jamnagar that run 24/7, transforming crude oil into fuel in an unbroken stream. A shining example of integration is the Amul dairy in Anand, Gujarat. It's a masterpiece. It masterfully links thousands of rural milk collection centers directly to advanced chilling, processing, and automated packaging lines. This proves a factory can be a powerful engine for both economic growth and profound social good. This model of integrated, efficient, and socially conscious manufacturing is now being amplified by government initiatives like Make in India and the Production Linked Incentive or PLI schemes, which are fueling a new wave of advanced factory development in sectors like electronics, pharmaceuticals, and textiles across the nation. A successful factory is born from a successful plan. Factory planning is the systematic, multidisciplinary process of designing the entire physical, operational, and human framework of the facility. It's not a static, one-time blueprint, but a continuous, feedback-driven activity, especially in today's rapidly changing world. The process involves several key steps, each one critical. First, a needs assessment. This is the foundation. What exactly are we making? At what capacity? What unique technologies are required? Planning for a biotech plant is fundamentally different from planning for a garment unit. Then, site selection, analyzing geography, infrastructure, and socio-economic factors to find the most strategic location. We'll dive deeper into this shortly. Layout design, creating a flow-oriented layout to minimize movement and eliminate bottlenecks, often using powerful simulation software to test and validate different designs virtually. Process planning, specifying the right technology and workflows, carefully balancing automation with skilled human labor, and integrating sustainability from the start. Resource planning, determining the exact mix of skills, training programs, utilities, and inventory systems required, not just for today, but for future scalability. And finally, compliance and sustainability, rigorously adhering to all environmental, labor, and safety laws, like the Factories Act, while embedding green practices like energy-efficient systems and waste minimization. Think of it like city master planning. It's a collaborative effort involving engineers, architects, supply chain specialists, and digital strategists to ensure all the districts or departments and roads or material pathways are perfectly integrated for resilience and growth. The choice of plant location is one of the most critical strategic decisions a company will make. It's often irreversible, a commitment of capital and resources with consequences that last for decades. Key factors influencing this decision include proximity to raw materials to reduce logistics costs and enable lean just-in-time inventory systems. Access to skilled labor, which is why IT parks thrive in Bangalore and auto component hubs form around Chennai. Robust transportation infrastructure. Hyundai's Chennai plant, for example, leverages the city's port to become a global export hub, a decision that shaped its entire business model. Nearness to major markets for faster delivery and better customer responsiveness. And, of course, reliable power and utilities, favorable taxes and incentives, and a stable socio-political climate. But finding the optimal location requires a deeper, more technical analysis. This isn't just about picking a spot on a map. It's a multi-criteria decision-making process. Companies perform granular cost structure analysis of both fixed and variable costs. They use logistics optimization models to map transport routes and calculate freight costs. They conduct deep labor market mapping to assess skill availability and wage competitiveness. They even integrate climate and disaster risk modeling to ensure long-term business continuity. Decision methods have also evolved. Planners use weighted scoring models to rank locations based on strategic priorities. They use the analytic hierarchy process, AHP, for structured, logical comparisons. And they use advanced GIS mapping to layer all this data visually, simulating scenarios to see how a location would perform under stress. The goal is to find the site that offers the most robust compromise between cost, risk, and future scalability. For large organizations operating nationally or globally, the challenge becomes even more complex. They face the multi-plant location problem. This isn't just about finding locations, it's about determining the optimal number of facilities, their individual capacities, and how to allocate product flows between them to minimize system-wide costs. This strategy allows companies like Sun Pharma and Tata Motors to be closer to diverse markets, mitigate risks from regional disruptions, and build a resilient supply chain. Underpinning all these decisions are rigorous economic considerations. Every potential location must undergo a detailed financial evaluation. This includes a comprehensive estimate of capital costs, the upfront investment in land, construction, and equipment, a detailed analysis of operating costs, the ongoing expenses of labor, utilities, maintenance, and materials, and a suite of financial calculations like break-even analysis, payback period, and internal rate of return, IRR. Let's walk through a practical example. A company wants to invest R60 crore to expand capacity. After calculating all the incremental revenues and costs, including non-cash costs like depreciation and the impact of taxes, they determine the annual cash flow is just under Rs8 crore. This results in a payback period of 7.6 years on an 8-year project, which is quite risky. More importantly, the net present value, or NPV, which measures the project's profitability against the company's cost of capital, is negative. Financially, it's a bad investment. However, a company might still proceed if there are overriding strategic factors, like blocking a competitor from entering the market. This shows that the final decision is a blend of hard numbers and strategic vision. Finally, we must consider plant capacity itself, the maximum output a facility can sustain. This isn't a fixed number. We have design capacity, the theoretical maximum, effective capacity, which accounts for realistic constraints, and actual output. Smart companies manage these levels carefully, building in a capacity cushion to handle demand surges and planning for scalable expansion. Now, let's step inside the factory. The way everything is arranged, machines, workstations, storage areas, is called the plant layout. It is the physical architecture of the operation, and it is fundamental to efficiency, safety, and even company culture. A good layout facilitates flow. A bad one creates chaos. There are 4 fundamental types. The process layout, where similar functions are grouped. It's highly flexible and ideal for custom work, but can lead to inefficient material movement as products crisscross the factory floor. The product layout, the classic assembly line, arranged sequentially for high-volume standardized products. It's incredibly efficient but highly inflexible. The fixed position layout, used for massive products like ships or aircraft that cannot be moved. The product stays put and all resources come to it. And the cellular layout, a smart hybrid where machines are grouped into mini-factories or cells, each dedicated to a family of similar products. This balances efficiency and flexibility. The choice of layout is dictated by the product. An automotive plant is a perfect example of a product layout, designed for uninterrupted speed. A garment factory uses a cellular layout for sewing to handle the high variety of styles and sizes. And a dairy plant uses a modified product layout with extremely strict hygiene zones and one-way flows to prevent any possibility of cross-contamination. Designing these layouts is governed by timeless principles: minimize material handling, ensure a smooth sequential flow of work, build in flexibility for future changes, maximize the use of all space, including vertical space, and above all, prioritize safety and ergonomics for the workforce. Layout is driven by the underlying production system. This is the broad philosophy of how resources are orchestrated to create value. Job shop and batch production are forms of intermittent production. Production is stop and start, organized around discrete jobs or batches. These systems are inherently flexible, perfect for high variety and customization, but often have higher per-unit costs and complex scheduling challenges. Think of a bespoke jeweler or a pharmaceutical company making different medicines in batches. Mass production and continuous production are the opposite. They are designed for high volume, low variety, and maximum efficiency. Continuous systems, found in sectors like steel or chemicals, are the zenith of flow, where the entire plant acts as a single, unbroken pipeline. They offer ultra-low unit costs, but are highly capital-intensive and vulnerable to disruption. A deep dive into the assembly line shows this in action. A product like a mixer grinder moves down a conveyor, stopping at each station for a specific duration, known as the takt time. Modern lines are enhanced with andon systems, a visual signaling system that allows any worker to flag a problem, empowering them to maintain quality without stopping the entire line. And they increasingly feature collaborative robots or cobots, designed to work safely alongside humans, handling repetitive or strenuous tasks. Today, the factory floor is powered by a digital thread that connects every aspect of production. Computers have transformed manufacturing from a manual, reactive process to a data-driven, predictive one. The flow starts with ERP software, the central business brain that takes sales orders and creates a master production schedule. This plan is informed by CAD software, which holds the precise 3D digital blueprint of the product. On the shop floor, a manufacturing execution system, or MES, acts as the nerve center. It receives the order from the ERP, translates it into detailed instructions for each workstation, and tracks progress in real time. At the machine level, IoT sensors are the eyes and ears, monitoring everything from temperature to vibration, predicting potential breakdowns before they happen, and preventing defects. This integration is also revolutionizing layout design itself. Computers allow designers to build and test a factory in the virtual world first. CAD software helps visualize the space and perform clash detection to prevent costly installation errors. Simulation software can run a full day's production to identify bottlenecks and test what-if scenarios. And a digital twin, a living virtual replica connected to the real factory, allows managers to monitor and optimize operations continuously. This leads to the ultimate in modern production, the Flexible Manufacturing System, or FMS. An FMS is a fully integrated system of automated workstations, robotic material handling, and a central control computer. It has the efficiency of an assembly line, but can switch between different products on the fly, making it a revolutionary solution for high-mix, high-precision industries like aerospace or even custom jewelry. Finally, none of this would work without a system to move materials. Material handling is the factory's circulatory system, ensuring the right part is at the right place at the right time. The choice of equipment, whether it's a simple forklift, a conveyor belt, or a fleet of automated guided vehicles, is a critical decision that impacts cost, efficiency, and safety. The selection depends on three key factors. First, the characteristics of the material itself. You'd handle fragile potato chips with a gentle bucket conveyor, very differently from 10-ton steel coils, which require a powerful overhead crane. Second, the characteristics of the plant layout. A narrow aisle warehouse needs specialized reach trucks, not standard forklifts. A multi-story facility needs elevators or vertical conveyors. And third, the production requirements. An automotive assembly line needs a continuous, high-frequency flow of parts, making automated systems ideal. A small workshop that moves a heavy mold once a day only needs a simple manual hoist. The right material handling system ensures that everything gets where it needs to be, safely and efficiently, completing the complex choreographed dance of modern manufacturing. From a strategic dot on a map to the intricate digital dance of robots and data on the assembly line, the modern factory is a marvel of planning, engineering, and technology. It's a complex, interconnected system where location, economics, layout, production systems, and logistics must work in perfect harmony. Understanding these core principles isn't just an academic exercise. It's the key to understanding the powerful engine that drives our global economy and shapes the world we live in.